Hey there, it's Dr. B here as usual, and it's time to learn how to ace that Module 3 quiz. I've selected several questions here that I believe will be relevant, and if anything seems difficult with these, then go back and review the core material that you just learned in order to master this topic. So here we go. Let's learn about the mole and stoichiometry. What do the terms mole and stoichiometry mean briefly? Now, I'd recommend you pause these videos and answer them yourself before you hear me do it. So that's what I think you should do. The mole to me is just a number, right? It's 6 times 10 to the 23rd, and anytime you have that many of anything, and we're usually talking about atoms, well, you've got a mole's worth. It would have a mass, and you'll see that mass written down throughout the periodic table. Very handy. Stoichiometry literally means element measuring, and it's the mathematics that goes along with mixing chemicals. And here we are. The mole is just a number, and stoichiometry means element measuring. What's the molar mass of aluminum chloride? Pause, I hope. Well, that means you need 6 times 10 to the 23rd molecules of aluminum chloride. And to do it in practice, all you have to do is find those average atomic masses for each element. Go to the periodic table, look for that number with the decimal places, and you'll see that for aluminum, it checks in at about 27. Now I'm going to round to whole numbers just to make things a little simpler. And chlorine, well, that one I'm actually not because it's right in the middle. That one is 35 and a half. So 35 and a half times 3 for the chlorines plus the 27 gives you a total of 133.34 if you're doing it precisely grams per mole. That literally means that many grams is a mole, or 6 times 10 to the 23rd molecules of aluminum chloride. Percent composition definitely shows up. Let's do ammonia. Well, pause it and do it yourself and see if your answer is the same as mine. It's nice to consider 1 mole's worth and see how much that weighs, and then just divide up the pie. Ammonia will check in at 17 grams per mole by virtue of the fact that nitrogen has an average atomic mass of just about exactly 14 grams, hydrogen 1 each, so 14 plus 1 plus 1 plus 1 makes 17, of which the vast majority is due to the nitrogen. I think that is 14/17. Get it? Dividing up the pie. 14 of the 17 total come from nitrogen. The rest, and 14/17 is 82%. The rest, I would just say 18%. I wouldn't even bother doing 3 divided by 17, but you should get 18% for the hydrogen, and that's the percent composition of ammonia. And there it is written out pretty precisely. Draw the dot structures of hydrogen, HNO. Look at that, HNO. Perhaps, I don't even know the name of that substance, but let's give it a try. CO2 and CHCl3. Okay, pause as usual. I'd recommend you memorize the simple idea that you should honk if you love chemistry. Hydrogen, oxygen, nitrogen, and carbon form 1, 2, 3, and 4 bonds respectively. Since almost every substance here is honk molecules, that'll save you huge amounts of time. Chlorine, all of the halogens form 1 bond. Now, if you do that, you can do these super fast, right? I personally would also write down somewhere that hydrogen has no lone pairs, nitrogen has 1, oxygen has 2, carbon has none, and the halogens always have 3. If you have that in your arsenal, you can whip these things together. So you just draw each puzzle piece, if you will. Hydrogen with 1 line, nitrogen with 3 lines and 1 lone pair, oxygen with 2 lines. And there's only one way to combine that, right? You can't put 2 bonds on hydrogen, so we'll put that at the beginning. We'll bond that to nitrogen. That's one of the 3 bonds it forms. The other 2 nicely connect to oxygen, and then you have HNO. I would add that lone pair to nitrogen and that lone pair to oxygen. Now, I think I have to show all 3 at once, so write that down. Hopefully that makes sense. Try CO2, and we'll start by putting carbon in the center. Another helpful hint for doing these is always put the most heavily bonded one in the center. That's usually carbon. So we'll put that in the center. put 4 bonds on it, but that doesn't make any sense because we only have 2 elements that are attached to it. I should say 2 atoms of oxygen that are attached to it. That leaves us with 2 bonds just hanging, but there are multiple bonds possible. So if we draw that double bond, just like we did with the N to O bond, if we draw 2 double bonds coming off of carbon, we should have it perfect. Carbon has its 4 bonds, oxygen has its 2 bonds, and don't forget your 2 lone pairs on each oxygen, and you are done with that one. Last one, CHCl3. Which one should you put in the center? The carbon, that's right, the one with the 4 bonds. Draw the 4 lines to it. Add your hydrogen on one side, chlorine, chlorine, chlorine on the other. Don't forget your lone pairs, and then convince yourself it's right. You'll be saying, hydrogen has its 1 bond, check, no lone pairs. Carbon has its 4 bond, 4 single bonds, check, no lone pairs. Chlorine has its single bond each time, yes, and 3 lone pairs, put them on it for each one, and you will be good to go. If you want to learn this deeper, why the lone pairs, things like that, listen to a previous video to cover it. But that should give us the structures here relatively quickly. There's HNO, which I wish I knew the name of. Here's carbon dioxide. There's chloroform. Continuing. If 2.4 grams of carbon reacts with hydrogen to form 3.2 grams of a hydrocarbon, what is its empirical formula? It sounds like it reacts exactly. It sounds like you have a hydrocarbon that consists of 2.4 grams of carbon and 3.2 grams of hydrogen. Worded a little funny. To solve these, and once again, I hope you paused, just figure out how many atoms of each. And for that, you really should use the mole. And then that'll give you the relative abundance of those atoms. Divide both sides by the smaller number, so it automatically turns 1 into 1, and you should get a nice clean whole number. I'll say what makes sense logically to me, and it's a fast way to do it. We have, I don't know, about 1/5 of a mole of carbon, since carbon checks in at 12 grams per mole. So we have less than a mole, right? 2.4 is less than 12. 2.4 divided by 12 would be how many moles, which is how many atoms you have. And hydrogen has much more, because hydrogen has 1 gram per mole. And we have 3.2 grams, so we have 3.2 moles of that. So we're going to have a much larger number for hydrogen than we do for carbon. Once we get those ratios, we divide them both by the little guy, and clearly carbon is going to be the little guy, 2.4 divided by 12. That should give us clean whole numbers, and we're done. And if you do that, wow, I didn't show any of the work, but it should be 2.4 divided by 12 for this one, 3.2 divided by 1 for the other one, and then divide both by the small number, and you should get a 1 to 4 ratio. This is methane, CH4. The next question asks us to calculate the mass percent of 5 grams of carbon that reacts with oxygen to form 10 grams of carbon dioxide. Now this question, I think, is one of the most challenging ones there. Let's try to make sure we understand it. You've made 10 grams of carbon dioxide. They say if you used 5 grams of carbon to start with, it should be too much. And we need to know what percent of it was actually needed. So if you made 10 grams of carbon dioxide, we'll figure out how many grams of carbon were required. The rest of what you used is your excess. Makes sense? Now, I don't think it shows the work here, so I'm going to walk through visually, and I hope this makes sense to you. I would say 10 grams of carbon dioxide consists of 12/44 carbon. Here's how I did that. CO2 consists of the carbon, which is 12 grams per mole, plus 2 oxygens, each at 16 grams per mole. Get that from your periodic table. And you'll convince yourself that the percent carbon in carbon dioxide is only 12/44. That's a little more than a quarter. So we'll only need about 2 and 0.8 or so grams of carbon to make that 10 grams of carbon dioxide. The rest would be your excess. And here, I think I'll try to walk through the math of what you could write for this. 10 grams CO2 times 12 grams of carbon for every 44 grams of CO2 would give you the grams of carbon required to make your 10 grams. And then that number, I'm going to estimate 2.7, say 2.7 divided by 5 would be the mass percent that you would react. It would be perhaps, I don't know, maybe 50, 55%. Let's see how we did just by estimating. And there it is. So, oh, look at that, 55%. That was just dumb luck. So here's the description. I hope that helps, and that's a relatively challenging problem. Next one, what's the molecular formula of ethylene? Empirical formula CH2 and molar mass 28 grams per mole. Well, this one is actually pretty quick because they gave you an empirical formula, which would, by the way, check in at 14 grams per mole. That's 12 plus 2. But you have a substance that's twice that. We have to keep that simple ratio and multiply it till we get to the actual molecular formula. And that's just called scaling. If this checks in at 14, but we need 28, just double everything. C2H4 would be the answer. And notice that C2H4 does have a ratio of 1 to 2 for carbon to hydrogen. Give the formulas for sodium chloride, sodium oxide, calcium fluoride, and sodium phosphate. What I recommend you do for each one of these is have your periodic table out, write each element, I should say ion, in order, write their respective charges by going to the top of the periodic table and see how the charges align, and do the drop and switch trick, which is just take the charge and put it down and to the right, or down and to the left for the other one, and then do a little logic test to make sure it looks reasonable, and you're good to go. Once again, I don't think I have the work shown here, so just listen as I describe each one. Sodium chloride, I'd write Na, and I put a +1 above it, because that is its typical charge. That +1 you're writing is just your own personal note. Chloride, I'd write the Cl, and I'd put a -1 above it. Now, I could just probably just cancel both of those at this point, because I know that the ionic compounds are always uncharged, and if you've got a +1 and a -1, there is no charge. They offset perfectly. +1, -1 equals 0. So NaCl, it really is Na1, Cl1, but they always ignore the ones, should work fine. Notice that the drop and switch would work. So if you wrote the +1 and the -1, here I am pointing to space, and if you just drop them and switch them, you'd put the +1 from sodium down and below the chlorine. You'd put the -1 for chlorine down and below the sodium. You get the same answer. Some people like that drop and switch. Some people like the logic method, but it's NaCl. Doing the same with sodium oxide, you'd get a different answer. Na gets the +1, but oxide, if coming from oxygen, check it out, that gets a -2. Drop and switch, you get Na2O, or you could do it by logic. Na with the +1 does not offset the oxygen with the -2. We need 2 of the +1s to offset the -2. Either way, the answer is Na2O. I'm going to do these last two just by the drop and switch method because it's faster. Ca gets a +2. Fluoride, that's F, gets a -1. Drop and switch, and you get CaF2. Sodium phosphate, Na gets the +1. Phosphate is not a phosphide. When you see something like a phosphate, when it ends with something like that, don't think it's just P3 minus. A phosphate is an entirely different thing. It's a polyatomic ion. Look it up and you'll see that it's a PO4 with a -3 charge. This drives some students crazy. That means you have one phosphate. PO4 is not like, 5 ions. It's just one thing that consists of 5 atoms. It's got a -3 charge, so write that PO4, put a -3 above it, drop and switch, and what do you get? Na3PO4. Give the mass and a number of moles of 1.204 times 10 to the 24th atoms of silver. Well, if it was 1 mole, then it would just be the average atomic mass that you look up on the periodic table, because that's what it gives you. So we need to see how many moles we have. Every time you have 6 times 10 to the 23rd atoms, that's a mole. So I would take 1.204 times 10 to the 24th and divide it by 6.02 times 10 to the 23rd. You'll get a nice round answer, which is 2. You have 2 moles worth. You might just recognize that 6 times 10 to the 23rd doubled is 1.2 times 10 to the 24th. You got 2 moles, so double the average atomic mass. And the answer is 2 moles, or 215.74 grams of silver. That's a lot of silver. Dot structure, shape, and resonance provide the molecular geometry, shape, and bond angles for carbon dioxide, methane, SO2, BF3, H2O, and NH3. There's a lot of work there. I am going to do this rather quickly. I hope it doesn't drive you crazy. Just watch the shape video to get more details on this. CO2 we showed before right here has 2 double bonds, and therefore I would call this an AB2 system. One thing connected to 2 others, and that can go linear. You know, you're always going to go for the most spread out you can. The answer is going to be linear. There are no lone pairs on carbon. If they were, they would have taken up space and bent that thing, but there's not. So it's just an AB2 system. It's linear. An AB4 system like this, that's what I'll always do. Just take these binary things, they're all binary, and just say one of these and how many of the other. AB4, you might think those are 90-degree bond angles, but you're not thinking in 3 dimensions. So we can take one of these and 4 of those and come up with better than 90-degree bond angles. We can spread them out to 109.5 by going tetrahedral. That's the answer to that one. SO2 you might think is a linear molecule, just like CO2 was, but without going into too much trouble, and that is a challenging one, it's shown in the video, you need to put a lone pair on the sulfur. That gives it a bent shape, and therefore this would be bent. It would be like an AB, the equivalent of an AB2 system with a lone pair. That lone pair takes up a shape, so you've essentially got 3 things attached to it, but one of them can't be seen. That's how I usually describe it. BF3 happens to be what they call an incomplete octet, but if you take boron, it tends to form 3 bonds. It has 3 valence electrons. And so we've got an AB3 system, 120-degree bond angles, works perfectly for that kind of thing. That spreads them out nicely in a triangle, and there you go. This is water. We should know the shape of water. Water, that oxygen is in the center. It has 2 bonds and 2 lone pairs. That means you have an AB2 system, but the 2 also have 2 things which occupy space, those 2 lone pairs. That means it's the equivalent of 4 things attached, 2 of which you ignore. So it's a tetrahedron, but you cannot see the lone pairs. They're not bonded to any atoms. Therefore, you end up with a bent molecule. Technically, the bond angle would go down from 109.5 for a tetrahedron down to 107 with 1 lone pair and 105 about with 2 lone pairs. The bond angles for these ones, I guess we gave them, right? This one's linear, so 180. Tetrahedral is 109.5. I think I mentioned that. Bent means it's going to be, I think, about 107. BF3, well, it's trigonal, so you get 120 degrees for each bond angle. Water, we said it's 105. Now ammonia, draw your nitrogen with its 1 lone pair and 3 things attached. Each of those are hydrogen. That means you have a tetrahedron, but that top dots, those top pair of dots, just cannot be seen. What do you end up with? A beautiful trigonal pyramid. They call this trigonal pyramidal. And those would be the shapes of and bond angles for each of those. These take some practice. How many reasonable resonance structures are there for phosphate and nitrate ions? Now, in the lesson, they point out that resonance structures are beyond the scope of the course, and then yet they ask this. So I would just memorize these 2 phosphate and nitrate ion resonance structures, or I would have them written down somewhere. And you end up with 4 for the phosphate and 3 for the nitrate. Since they say it's beyond the scope of the course, I'm not going to go into any more detail. Bond types and common acids. What is the bond type and the name for these? Now, bond type's good to know. If it's got a metal present or it's an acid, we call it an ionic bond. If it's got no metal present, these all look like, I don't know why I said bond type. I don't even think they're going to ask the bond type. These are all just acids, and so let's just give them their common names. There's a list of them on a previous slide. I'd recommend you memorize them. There's 6 strong and some weak. This one checks in at, hey, maybe let's see if you got this right. Did you say hydrochloric acid? Did you say sulfuric acid, nitric acid, acetic acid, Phosphoric acid. Ooh, I don't even know if that one was on the list. Hydriodic acid, the hello molecule. I'll say it again. It's not hydroiodic, it's hydriodic acid. I've worked with this, probably the scariest molecule I ever worked with in my life, hydrofluoric acid, and this one is hydrochloric acid. This took a while, but this completes the Module 3 quiz review.